So section 4.1 is going to be a 2-day ordeal, and we're going to stop after this page for the first day. The graph of a polynomial is a smooth, continuous curve. A smooth, continuous curve. That means no corners, can't have any right angles or anything like that. No cusps. Okay, a cusp in a graph would be something that goes like this. It kind of like hits a peak and comes back, like a corner, really. I guess by no corners, I mean, no right angles. Or no gaps. We saw gaps when we were having like piecewise defined functions, something like that. Can't have any gaps. A smooth, continuous curve. Okay, a simpler version of a polynomial is a power function. It's simply a polynomial that just consists of one term, like y equals 3x to the fourth. See, it doesn't have any terms after that. That makes it a polynomial, but because it's only one term, we'll actually call it a power function. Or y equals negative 1/2 times x to the fifth, or y equals x to the 11th. All of those are power functions. Okay, now because polynomials have a degree, a largest exponent, sometimes it's odd, sometimes it's even, there are some graphical characteristics go with that. So, we're going to talk about some properties when we have odd exponents versus even exponents. The graph of a power function will be symmetric with respect to the origin, of course, if it's an odd exponent, and the y-axis if it's an even exponent. These are like the parabolas, and these are like the swooshies. The domain for the function is all real numbers if the exponent is odd, and it is also all real numbers if the exponent is even. I can put any x I want into. The range is different though. Look what's going on here. I can have negative numbers and positive numbers. So the range, if we have a polynomial with an odd exponent, is all real numbers. All y values get used. But for this even situation, that would be bracket 0 up to positive infinity. We don't get any negative values when we use an even exponent. You know that. And then one more thing. In addition to the origin, every single power function will have a point at the origin. Put in a 0, get a 0. And if you put in a 1, you get a 1. Well, I guess that one's not going to be 1. I guess I mean the parent functions. There will also be the point, if it's odd, we'll have the point negative 1, negative 1. If it's even, we'll have the point negative 1, 1. Negative 1, 1, negative 1, negative 1. That's for the parent functions. Now there's a thing called end behavior, and I don't know if you've seen this before, so let me talk about what this means. If it's an odd kind of a exponent, it's a swooshy looking graph, right? It looks like a swooshy. So I'm going to draw a little swooshy right there. This is how the end behavior is written. As x approaches negative infinity, f of x approaches negative infinity. See what's going on here is as the x's get way out here and go way far left, the y values go way far down. As x approaches negative infinity, that's this negative infinity out here, the y values are approaching negative infinity. And same thing on the other side of the graph. As x approaches positive infinity, what's going on is the graph continues to go up. In fancy calculus terms, it goes up without bound. And so as x approaches positive infinity, y approaches positive infinity. Now if I have an even function, like the x squared or x to the fourth, there's a little bit of a different behavior. As x approaches negative infinity, f of x approaches positive infinity. That's different from the last one. As x goes towards this negative infinity, the y values just keep going up. It goes up towards positive infinity. And as x approaches positive infinity, f of x also approaches positive infinity. As the x's go towards larger and larger numbers out here, the y values just get bigger and bigger and bigger. All right, guys, that's the end of the first day of section 4.1. Your homework's on my math lab. Have yourselves a good day. More fun tomorrow.